Hey everyone, I'm Rishab Bahal. I am a software developer working basically in full stack development, but I have from last 1 year also doing AI integration. And working in a startup, I have wore multiple hats, and I happen to work with Whisper and fine-tuned it for radiology terminology, though that project never got off-shelf because of a lot of red tape in the medical field. But I explored a little bit of Whisper and how to fine-tune it, and some of the parameter efficient fine-tuning techniques. So I'm going to discuss some of that today. And basically, I fine-tuned Whisper in one of the low-resource language. So before I go further, I would like to know how many of you are aware of the OpenAI's Whisper model? Less than 50%. So for those who don't, I will start from scratch. So Whisper is a kind of encoder-decoder model, very similar to the GPTs, and if I say in a layman's term. So GPTs generally take text as input and text as output, whereas Whisper is a model which takes audio as input and gives text as output. So basically, it is for audio transcription, automatic speech recognition, and transcription. Other than transcription, what else Whisper can do is speech translations. And it can also identify different languages if you are speaking something, if set in the multilingual mode. The Whisper model has been trained on 680,000 hours of multilingual data. And it comes in 6 different sizes, while the turbo model was released very recently. What most people don't know is how the pre-training of the OpenAI's Whisper has been done and how it is divided. Though it says it is a multilingual model, the 65% of the data on which it has been pre-trained is English language audio as well as the English transcriptions. And out of the rest, 35%, roughly 18% is non-English audio and English transcripts. And while the final 17% represents non-English audio and corresponding transcripts. So if you're talking about a language such as Thai or Hindi, which has their own transcripts, it has been trained only 17% of the pre-trained data. So if you take a Whisper model such as a base Whisper model, it doesn't perform that well with these languages, although it's very robust for English. Me being born and raised in Delhi, India, my mother tongue is Hindi. So I'm going to take it as an example to show you further. So this is a Whisper UI for a Whisper-based model, the original model, which is only pre-trained on the original data. And I have an audio clip where I'm speaking in Hindi and introducing myself.
मैं दिल्ली भारत का निवासी हूँ। मुझे कनाडा में 5 साल हो गए हैं और मुझे ओटावा में 2 साल हो गए हैं।
What basically I'm saying is that my name is Rishab Bahal. I am from Delhi, India. It has been 5 years being in Canada, and it has been 2 years being in Ottawa. And the problem that I face with the Whisper-based model, for this example I have taken, generally the transcriptions are not very well. They're not even in Hindi script. They generally take an English script and show it to me, or sometimes it shows me garbage data, or sometimes it takes a different dialect of Hindi, such as Urdu, which is very similar to Hindi, and shows me. You see, it is just rubbish that came out. So I'm going to try to improve it. And what I did is I fine-tuned this model. So I'm using Whisper base for all the experiments, which is a 74 million parameter model. And for fine-tuning, I used a data set called Mozilla Foundation Common Voice 13, which is available on Hugging Face. And so this model has multilingual data, but I took specifically Hindi-based inputs. So it looks something like that. It has a lot of metadata though I pre-processed it to have only audio and sentences in it. So it's approximately 13 to 15 hours of training data and 4 hours of test data. On full fine-tuning the model, it took me about 4 hours and 44 minutes. And it gave me a word error rate. So I'm using, for evaluation metrics with the transcription, I'm using word error rate. And it gave me about 46%. So if I go and show you the original notebook, I have this model which gave me about word error rate of 46. And if you check, it took me about 4 hours and 44 minutes. Then I wondered if there's an efficient way to do it. And that's when I came to parameter efficient fine-tuning techniques. Why I came there? Because there are a lot of problems with full fine-tuning. So I took a base model with 74 million parameters and took me about 4 hours and 44 minutes, approx 5 hours. So if consider the fact that if I'm going to take a model such as Whisper Medium, which has about 10 times the parameters that a base model has, it's going to take me 10 times the computation power and also going to take 10 times the time, approximately. So that's why we go to parameter efficient fine-tuning techniques. And how many of you know what is PEFT or what are parameter efficient fine-tuning? For those who don't, these are the techniques or some methods which focuses on reducing the number of parameters we need to fine-tune to get the same result as full fine-tuning the model. So it has different methods, but I'm going to focus on only one method today, which is low-rank adaptation. And low-rank adaptation works on rank decomposition. And I'm going to give you an idea what is rank decomposition and how it works. So any neural network, within the hidden layers, there are weights that we need to tune to get our desired results, right? And these are represented by matrices. So in reality, these matrices are floating point numbers, and these are huge matrices. For simplicity, I took a 3x3 matrix, and so I took a 3x3 matrix, and it has only integers. The reason I'm using only integers, just for the simplification, so if you see, there are 9 values within a matrix, but that can be represented by, if I take only one row and one column, I can reproduce the whole matrix. So I don't really need the whole matrix, and I don't need to fine-tune the whole matrix. I can take one specific row and one specific column, and I can tune it and reproduce the whole matrix. That's the idea behind it. And of course, in the real time, it works on floating point numbers, and the matrices are generally very large. So this rank decomposition reduces the number of parameters that we need to fine-tune. So if you see this chart, and you see that if I'm taking a 7 billion parameter model, and if I take rank 1, I just need 167,000 parameters that I need to fine-tune. And even if I take a rank as high as 512, I just need 86 million parameters to fine-tune with respect to a 7 billion, which I would have used for full fine-tuning. Now, I'm going to take you to the notebooks. So I already showed you the full fine-tuning. And as I said, rank is a very important parameter for low-rank adaptation fine-tuning. And how do you decide a rank of a model? Now, ranking generally take place as a multiples of 4 because it helps a hardware to be more efficient and efficient in calculation. So I started with rank 20 for my use case, and the trainable parameters came out to be 737,000, which is approximately 1.0054% of 74 million parameter model, which is a Whisper-based model, right? And it took me about 12 minutes and 3 seconds to fine-tune those models. And then I pushed it to the Hugging Face hub. Now, when we push this model to the hub, it's not the model we are pushing it. What we are actually pushing is the adapters, the difference that we have fine-tuned. And the way Whisper LoRA works is we fix the pre-trained model. We take the fine-tuned adapter, superimpose them, and then get the output. So basically, I took it with the rank 20, I took it with rank 24, and I took it with rank 28, and took it with rank 32 to see the differences. And here you can see how the time differences and the word error rate differences that I got, and the number of trainable parameters that I used. For full fine-tuning, it took me 4 hours and 44 minutes to fine-tune the whole model. And the word error rate was only 46%, which is not bad. And I can show you a demo how it is working now when it's full fine-tuned. So I'm going to use the same audio that I used before, which was giving me this garbage output with a full fine-tuned model. And once I submit it, I do get the Hindi transcript, which is okay. And still I have some spelling mistakes though with the nouns, but it's still better than what I was getting here. And finally, when I fine-tuned with the LoRA techniques, with 20, 24, 20, and 32, you see that word error rate is 52.25% when I took the rank 24, and that's why I decided to go with it. And if you see, I just trained 1.2% parameters, still I got a word error rate of 52%, whereas full fine-tuning gave me about 46. So why would I not go for a low rank adaptation in this case, rather than full fine-tuning it? And if you see a demo of how it works with the LoRA, again, I'm going to use the same audio, and you will see I will get comparable results. Very close to what I got with full fine-tuning, even after tuning for about 12 minutes and about 1.2 parameters only. So that was all for the demo. I'm open to any questions if someone has.
Thank you. Can you go to the notebook for just full fine-tuning? Yeah, I think, have you tried less steps? Because I think it's overfitting right now. Training loss is going down, but the validation loss is going up. I wonder if you train less steps, because I think even 10,000 steps is already overfitting.
Yeah, I think reducing the steps would have stopped it with about 45, rather than, because overfitting will increase the whatever rate. That's what you're saying?
Yeah, like here, the validation loss start from 0.41 and it goes up.
Mm-hmm.
Where training loss is going down,
Mm-hmm.
which means it's overfitting.
I haven't tried that for now, but I will consider it. Thanks.
Alright, I have one question myself. So, based on my experience working with Q&A, so quantized LoRA numbers, I often find trying to fine-tune the data, basically it overfitting my data. So it works well, and in new data, I will completely forget all the English data. So I was working with large numbers before. So, with your approach, does it signal works fine in English or other languages, or now specifically according to me?
So when I'm talking about the LoRa concept, it works on transfer learning. And what transfer learning is that you are already pre-trained on English, and if you are giving something a different accent or a vocabulary in English, it works very well. But if you are taking a completely new data and try to put it on it with LoRa, what will happen, the ranks, it will not perform very well, and you keep on improving the rank. So for in my example, you see, I got 131 word error rate, which is like a disaster. And something like that will happen for the initial ranks, and you will have to keep on improving the rank in order to get a better fine tune, and eventually you will reach a point where the rank is equivalent to full fine tuning. So basically, if you have completely new data and you're not doing transfer learning, you will have to do a full fine-tuning eventually, even because full fine-tuning is a subset of LoRA technique.
Thank you for your presentation. Do you use a standard data set or you prepare your own data set?
Sorry?
Did you use a standard data set to fine-tune the model or you prepare your own data set?
No, I didn't prepare my own. I used one of the data sets available on Hugging Face.
Hi, that was a nice presentation. So,
Thanks.
in comparison to Whisper, have you tried out Levin Labs product's version 2 TTS? And if so, did you notice any significant difference aside from the transcription itself?
You mean the 11 labs to fine-tune it, or just the model itself?
The model itself.
I have tried 11 labs. I also have tried DeepGram. So there are already tuned models, but there can be use cases where you might want to fine-tune your own model. So of course, this is just a presentation. That's why I took one language and showed it. But there can be use cases where you want to fine-tune your own model, and that's not available. So yeah. But of course, for Hindi and other stuff, there are already existing models which perform well better.
Hi. Interested to hear one of your parts. You said full fine-tuning was a subset of another kind of tuning? Sorry, I didn't hear you.
Okay, so I was saying, so when we are using LoRa, so we are using ranks. So we start with initial rank 1 or maybe rank 2 and go further. But rank can go as high as what one matrix size is. For example, if within a neural network, 100 by 100 matrix is representing one of the hidden layers. So maximum rank that you can go till is 100. You can't go any further. And once you reach the 100 rank, basically it's not anymore LoRa. It's basically you're full fine-tuning the model.
Okay, I understand. Thanks.
Hi.
It seems counterintuitive that the word error rate go up as you raise the ranking. Is that to be expected?
It is not to be expected. So usually when you increase the rank, the word error rate should go low, but there is another parameter that I didn't show you. So that's called LoRa alpha, which is the learning rate. So I'm also changing the learning rate along with it. Keeping the learning rate consistent would have improved the word error rate. But since I'm also moving that, so that's why you can see the difference.